All right, so as we begin our review for rotational dynamics, there's a couple things that is very important. What you want to do is look at your equation sheet. On the IB exam, you're given quite a few equations to help you out, but there's a lot that aren't given. And what we're going to do in this clip is, well, really in this review, is look at what is expected for you to know by heart, and then how to go about looking at rotational dynamics in our review. And this is a very critical section because this is our option, which is part of paper 3, and you need to be really solid with rotational dynamics and thermodynamics. So the first thing that we want to talk about is average angular velocity. How many radians do you cover in a period of time? And this will give us our average speed. So we want to review what a radian is, right? So you got a circle. The radius is here. So if this length matches the length of the radius, that is a radian. So if the radius is, I don't know, 1.5 meters, this length right here would be 1.5 meters. And then another length here of 1.5 meters would be the second radian, then a third radian, then a fourth, then a fifth, and then a sixth, and then a little bit more, 0.28 radians more. Which the full all the way around is 6.28 radians, which is 2 pi, which is 360 degrees, right? So 2 pi radians is 360 degrees. Now, another thing that they expect you to remember is alpha, which is the change in angular speed over time, which is radians per second squared. So they expect you to remember that. How does the angular speed change? If something is spinning and it's slowing down, you would have a negative alpha value as it slows down. Now, the equivalent in position, right, is the radian. In linear velocity, it's the angular speed. And then linear acceleration is angular acceleration. Now, with those, we have the kinematic equations. This one, and this one are our key ones here with the correspondence of this, right? So for position, we're dealing with how many radians. The initial speed with the initial angular speed. We have time, and then we have alpha, which is the angular acceleration, and then the linear acceleration. Here, final speed, final angular speed, initial velocity, initial angular velocity. Alpha is, again, acceleration. Angular acceleration is linear acceleration. So we have the corresponding equations. Now, they do give you these. They give you this one, and this one on your equation sheet, which is helpful. And so you can use that for any situation where you're accelerating. Now, let's go ahead and practice this. See if you can use the equations here to calculate how many revolutions the disk goes before stopping. And the initial angular speed is 24 radians per second. The angular deceleration, so alpha, is -3 radians per second squared. The initial angular speed is 24 radians per second. And we want to know how many full revolutions. Well, we can't really find that out yet. We can find out how many radians, though, and then once we know that, we can figure out revolutions. And remember, one revolution is all the way around, which is 2 pi. And then you can find time as well. So see if you can use the kinematic equations to solve for that, and when you're ready to check, you can hit play to continue. All right, so we should get, for our angular displacement, 96 radians, which we convert to revolutions, which we'll do in a second. We can get a time of 8 seconds using another kinematic equation. And so, 96 radians. So 2 pi radians, right, which is all the way around, is one revolution, one full revolution. So this is going to make a full 15.28 revolutions as it spins and slows down to a stop. The final angular speed was 0. All right, so one of the things that's critical here is the intuition behind this, because, again, you're not given the equation here. You need to know what's going on. If a wheel spins 5 radians, delta theta is 5 radians. So the radius is 0.6 meters, and therefore the length there, 0.6. 1, 2, 3, 4, 5. It's going to go 5 radians around. Now, if the radius is 0.6, if this right here is 0.6, that length right here is 0.6. And then this length right here is 0.6, right from here to here. And then this is 0.6, and this is 0.6, and then this is 0.6. So if each of those are 0.6, 0.6 plus 0.6 plus 0.6 plus 0.6, and we do that 5 times, we're going to get the total length, which is 3 meters. So we can get the linear distance by multiplying the radians by the radius. And that will tell us how far linearly it will go. Now, again, this is not given on your equation sheet. This is definitely helpful to know, but you should know how to get there, you know, based on all this, okay? So it's gone 3 meters across the ground. Now, let's take a look at this one here. We have 4.3 radians per second is the angular speed. It's going at constant speed. Therefore, there's 1 radian, 2 radians, 3 radians, 4 radians, and 0.3. So how far linearly has it gone? Well, if we know that the radius is 0.8 meters, it's gone, you know, 0.8 plus 0.8 plus 0.8 plus 0.8, and then, you know, 0.3 radians times 0.8 is 0.24. So the total length, if we add them up, is 3.44. Now, it turns out then if that's in a second, it'd be 3.44 meters per second. That's the linear speed. So we get the value here. If we take 0.4 or 4.3 times the radius, we can get the linear speed. And this is another equation that's not given. We take the radius by the angular equivalent to get the linear. Now, there's 3 of these. We have the first one. We take the radius by the angular equivalent to get the linear. We have the radius again by the angular speed to get the linear speed. And then finally, the radius times alpha to get angular acceleration. So it's important to be able to go back and forth. All right, so this is a good practice one with graphs, just like we did with, you know, linear graphing with translational kinematics. It's important with rotational as well. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. One of the things that was asked in class, the time is down here, and then there's a backslash in seconds. So these are each 2 seconds, 3 seconds. Over here is omega, which is the angular speed. So this is 12 meters or 12 radians per second. And therefore, that's why the units are giving as a 1 over a second, because the radians is unitless. It's a 1 over a second for angular speed. So we know that acceleration is the change in angular speed over time, which in this case here, we get -3 radians per second squared. And therefore, we can get the, yeah, we know the acceleration. That's part A. Now, part B, what is the angular displacement of the mass? Well, we know omega times time will give us delta theta, which is how far it goes. And these are on the x and y axis. Therefore, we can get the area. And if we get the area, that will give us 24 radians. That's how far it goes. Now, you could have used the kinematic equations too, and that would have been fine. All right, so now let's take a look at this here. We've got a cylinder. Axis of rotation is in the middle. If we applied a force on this and it's a frictionless surface, what is this mass going to do? Well, if it's frictionless, it's just going to slide from left to right. And that kind of makes sense. Now, if we apply a force at the top and it's frictionless, it's going to start to spin and get faster and faster and faster. Now, the way that we'd figure out what's going on with that is with torque. We have a force over displacement times sine of theta. In this case, this is 90 degrees. Perfect torque. The force is 30 newtons. The lever arm is 0.2 meters. The amount of torque would be -6 newton meters, and that would be making it go faster. Now, what if we deal with this situation here, where we apply a force through kind of the middle part? Well, one of the ways to find out what the torque is to draw a line from the middle over to the edge here and take this force, which is this vector right here, and break it into its x and y components, this component and this component. Now, which of these components are perpendicular to this lever arm here? What's this one, right? So if we use our math, let's say this is 18 newtons here, this is 18 newtons here, and the angle here is 28 degrees, which we would need right here. And the opposite side is 8.45. We can use that as well as the length here. Let's say the length is 0.4, this is 8.45. We can find out how much torque there is. Now, what we can also do, if we wanted to instead, is just use this full 18 newtons, but use this short lever arm right here. And therefore, if it's 18 newtons, this is 18 newtons, we have the length of 0.0188, we would get the same amount of torque. So either way is okay. Sometimes one is more convenient than the other. This is similar to where, you know, we're dealing with the ladders and breaking down the ladder itself instead of the force. It just depends on the situation.